Okay, welcome to today's lecture. So today I'm trying something slightly different. So rather than recording using PowerPoint, I will now record using Zoom. And the reason is that I'm taking material from many different presentations, and some of them are not available in PowerPoint format, but rather in PDF format. So this would actually be quite similar to the way that I would give this lecture if it were live. So today the topic is about problem-solving paradigms. So what I'm going to talk about here today is basically given an overview of many different ways of solving problems. Simulation, greedy dynamic programming, divide and conquer, complete search, branch and bound, probabilistic search, and so on. So hopefully this will give a good introduction to different ways of solving problems. So the first type is simulation. So basically this is the type of problems where you just do exactly what you're told. So there is a problem statement and you basically have to follow it. It could, for example, be to simulate a robot. It might be that you're given a sequence of commands, and if the robot carries these commands, will it achieve certain things? For example, will it be able to leave a maze without running into any obstacles or something like that? And then you basically have to write a program to carry out these instructions and see what happens. And actually, you have already seen several of these kind of problems so far. So for example, the set stack computer, that was one of the exercises for last week, was very much about simulation. You basically have to implement this particular computer. And the same with introspective caching. So again, this was about figuring out what elements to keep in the cache, and then to simulate the computer doing these operations. And chopping wood, here actually the simulation was kind of reverse, because you needed to figure out what you needed to do. So in some sense you needed to figure out what was the program that got this result. So this is one common type of approaching a problem. For these kind of competitive programming situations, it's not that common, but in many other cases. So actually one very much related approach is complete search. And here the challenge is that either the problem is very small, or you basically have to try every possible combination that there is no structure, no other information. Then complete search is a structured approach to trying every possible combination to figure out what works. And here, in order to determine whether this is a reasonable approach for the particular problem, you really need to be careful about the maximum size. So the number of possible solutions or possible instances there is. So this will be very important. So you really make sure that you can fit it in the time allocated. So remember, roughly 100 million operations is what you can do. So how can we then do it? So there are basically two ways of doing it. So either we use iterations, so basically enumerating everything, or we do recursive backtracking. So in iterative complete search, the idea is basically to use nested loops to generate every possible complete solution and then filter out the valid ones. So this is often called generate and test, or generate filter type of approaches. So of course you can use standard for loops. So for example, a very simple example would be to solve a Diophantine equation. So for example, the question is x plus y equals to 5. Find all the solutions to this. Then you basically have to loop over x, you have to loop over y, and for every combination that becomes 5, you print that. Often it might be that you have a more complex data structure. or you want to use permutations. So for example, assume that we have 5 variables, each having 10 different values. Then we can generate all the permutations. So, or sorry, my apologies. So that's a different one. But a permutation is basically you have a sequence. So, for example, you have to check the order. So the order that you need to do something, you have 10 different things, and the question is in which order should you do these 10 different things? And then it's very convenient to basically test all the permutations of these 10 variables, and that you can do in C++ using next permutation. So you basically just initialize the vector, and then you iterate over the next permutation to find the solutions. So examples here could be, for example, the n-queens problem. So there in the n-queens problem, you basically have to position one queen in each row and column. So you can, for each row, represent which column is this queen in. So this would then be, for example, if there are 10 queens, it will be a vector of length 10, where each number has to be there exactly once. And then you can iterate over these permutations and just check for diagonal conflicts. Another very convenient technique is, for example, if you have subsets. So, I mean, we have seen this knapsack problem, and then I will talk more about the knapsack problem later. So basically, you have a set of items, and now you have to determine which subset of these items should you select, such that the total weight of these items is lower than the capacity of your knapsack, and the value of these items is as high as possible. And this we can do very nicely with bit sets. So in this case, each bit in your number represents whether a particular item is included or not. So if you have, for example, 16 items, you can then iterate over, loop over from 0 to 2 to the power of 16, where 0, of course, is that no elements are included, and 2 to the power of 16 is where every, or rather -1, then every element is included. And so this is a very efficient way of looping or iterating over subsets. The other technique, which again is very general and very useful, is called recursive complete search or recursive backtracking. And here what we do is that we extend a partial solution with one element at a time until a complete and valid solution is found. And this, as I said, is often called recursive backtracking. And to make this more efficient, we want to use what we call pruning. So this means that if we can determine that by continuing down this path there is no solution, then we can stop computing this already. There is no point in continuing until we have a complete possible solution. And here a good example is again n-queens. So basically you can place the first queen in the upper left corner. So the queen on row 1 will be in column 1. And then we have the first step in our partial solution. The next step in our partial solution is to fill the second row. And here we can see, of course, it cannot be in the first, it cannot be in the second, because there is the... So actually, normally the way we would do this is that we would basically just start from 1. So then the first step in this backtracking would be to try to place the queen on on row 2, column 1. But there is a conflict, so we can prune there is no point in continuing. We then backtrack, which means that we try the next, which is to place it in the second column. Here we have a conflict on the diagonal, so again we cannot do it. And then we place it on the third column, and that works. So now we have a queen in the upper left, we have a queen in the third column on the second row, and then we can proceed to the third row. And here we can see we cannot place it in 1, we cannot place it in 2, we cannot place it in 3, we cannot place it in 4, but we can place it in column number 5. So now we have on the third row the queen in column 5. And then the fourth row, we can now place it in column 7. and now we have to place the queen on the 5th row. And now we come to the conclusion that there is no row where we can place this on. Or maybe we can place it on the 2nd row. But anyway, at some point you will reach a point where you cannot add the queen anymore. There is no position on this particular row where it works. And then you need to backtrack, which means that you need to change the previous solution. So you need to change that and basically move the queen, for example, 1 step to the right, and then restart with everything below it. So this is extremely general technique, which basically allows you to solve any problem where you can enumerate these partial solutions. And to make them efficient, you should have this kind of pruning, so you can easily remove, so as soon as possible, you can remove the rest. So very useful, very good technique. Also quite easy to implement. Related to this is also branch and bound. So basically this is when you can partition your search space, and then you can find a solution for one of these partitions. And then for example, you can use this solution for the for one partition to kind of bound. So for example, we might be finding we have some kind of search problem, and we want to find the shortest time it takes to do something. And for example, if we have found a solution which takes time 15, and then we kind of continue our search and we reach a partial solution where the total time is now 15 or more, there's no reason to continue down that branch, because that will always increase the time it takes. So there we basically can prune and we can remove everything below. And this technique is often very good to combine it with greedy solutions. So you can use a greedy solution to find an upper bound or a lower bound, depending on your system. So basically you're trying to improve the bounds within which the optimal solution will be. And then you can use these bounds to prune trees or prune parts of your search space which cannot lead to a better solution than what you already found. And then when you're done, or the upper bound and the lower bound are equal, then you're done. And this is very extensively used in optimization. And we have also used it for our own research to develop state-of-the-art algorithms for solving very complicated and large combinatorial assignment problems, or combinatorial optimization problems with certain structures very efficiently, or as efficiently as you can expect, given that they're NP-hard problems. And of course, you may use a number of different pruning techniques again, so that you can, for example, do approximations, and using these approximations to approximate the upper and lower bound, so that you can use what we already know to further improve the quality, or rather reduce the time it takes. So it's really about minimizing this subset of total search space that you really try, and to focus the search on those areas in the search space where you're most likely to find a solution. Again, very general. I would say that these are not that commonly used in competitive programming. There, it's much more common to use this backtracking and complete search, for example. Okay, so now we come to the next paradigm, which is then greedy algorithms. So a greedy algorithm is an algorithm that, if you make locally optimal choices in each step, it still will end up in a globally optimal solution. So for example, an example would be this interval partitioning that we had in one of the labs, where you basically have to select a subset of intervals so that all the intervals cover a particular area or line. So there you could always choose the next interval such that the end time was as late as possible, and then that was agreed choice that would work. And in order for a greedy algorithm to work, there are two properties that it needs to have. First of all, it needs to have an optimal substructures, which means that an optimal solutions contain the optimal solutions to subproblems. So for example, I mean, if we have, so the solution to a problem of size n will contain the optimal solutions to all the smaller problems. So every problem of size 1, 2, 3, 4, 5 up until n. So this is the first, so it's called optimal substructures. The second one is that it has to have a greedy choice property, which means that if we extend a partial solution, we will get the optimal complete solution without considering previous choices. So it means that basically we can extend this one step at a time without having, there is never a chance that the previous choice need to be remade. And in some sense, you could think about this in terms of logic. So I mean, logic is monotonous, which means that if you add facts, you never remove things that previously was true, will still be true. So the more facts you add, you can never make something that was previously true false. So basically, it's similar here. You can add more information, but you cannot make a previously optimal solution suboptimal. So some classical examples are coin change. However, not in every possible currency, but if you have certain currencies, then we have this. So for example, you have, I mean, standard like 1, 5, 10, and so on. I mean, if you have that kind of, then you can always make a greedy choice that taking the largest denomination until of the available ones, and then you will know you will get the smallest number of coins. And as I already mentioned, greedy algorithms can be useful as heuristics. So just getting an upper or a lower bound to a problem, and then you can apply branch and bound or prune based on this information. So that's one technique that's very useful. So actually now I will try to switch presentations. So what I will do is now just give you an example of this coin change. So this are some very nice slides by John Kleinberg. The slides are from by Kevin Wayne, but the kind of content is taken from this book by John Kleinberg and Eva Tardos. So here the coin change problem is given currency dominations 1, 5, 10, 25, 100, devise a method to pay amount to customers using the fewest coins. So what you want to do is that you want to give the customer their change, but you want to use the fewest number of coins. And here, for example, we have 34 cents. Then we will always select the largest denomination we can use. So in this case, it's 25 because 100 is too high. We use the 25, and now we have 9 left. 9 is more than 100, less than, well, 100, 25, and 10 are more than 9, so we cannot use them. So instead, the largest one is 5, and then we have 4 left, and then we need to use for 1 cent. So this is then the optimal result, and we can do the same for any other number. So actually what we do here is that we just sort the n coin denominations And then we just start from the back, from the largest, and then we find the largest index k such that the value of that coin is less than or equal to the amount we should return. If there is no such k, so it means that then there is no solution. And I mean, if there is like a 1 cent coin, this will of course never happen, but assume that there is only 2 cent coins or 2, 5 and so on, then this might be the case. Otherwise, we reduce the amount with the denomination of the coin, and then we continue. So this is then a optimal solution. Why? So basically, we can just try something. For example, that the number of pennies will always be less than or equal to 4. So we know that that's a property, because if there are 5 pennies, they will always be replaced by nickel. And same, we can also prove that there will always be at most 1 nickel and at most 3 quarters. We can also prove that the number of nickels plus the number of dimes always have to be less than 2. Because if there are 3, I mean, we know there cannot be 2 nickels, so then it has to be 1 nickel and 2 dimes. And of course, that is 25, so then it's a quarter, and so on. So we can prove a number of properties. And then we can use these properties to also prove that this cashier's algorithm is optimal for US coins. So of course, the next question then becomes, is this optimal for any set of denominations? And I mean, as I've already said, that's not the case. So for example, this US postage stamps, which is to me really weird, 1, 10, 21, 34, 70, 100, 350, 1,225, and 1,500 is not optimal. And we just see that by looking at, for example, if we want to send something for 140 cents, then using this algorithm, we will select 100, we will select 34, and then we'll select 6 1 cent stamps. While the optimal solution here is using 2 70-cent stamps. So this is clearly a counterexample where this is not the case. Interval scheduling already talked about, so I suggest that you just go through these slides yourself to go through this example yourself. So the next item is divide and conquer. So again, I will use their slides. So divide and conquer is again extremely general approach. So basically the problem here, or the approach here, is to break down the problem in 2, usually equally, or I mean at least 2 subproblems of the same kind. So each of these 2 subproblems are now problems of the same kind, but much, much smaller. And then you solve this recursively. So that's basically the conquer step. You divide and then conquer. So you solve these each subproblem independently. And then you need to combine these partial solutions into a global solution. So that's so you break down the problem in smaller parts, solve the smaller subproblems, and then reconstruct or compute the final result based on that. So the most common way of doing this is to break a problem of size n into 2 problems of n half size. And then you solve these separately. And if you can combine these 2 solutions in linear time, it means that we can actually solve this problem in n log n time. Because of course, the number of times we need to use this linear solution is logarithm of n, because that's the number of time we need to break down the problem. So if we were to try every possible combination, then it would be n squared. But by doing it in this fashion, we save a significant amount of time. So one very nice and common example of this is using sorting. So it's an approach called merge sort. So in this case, we're given a list of n elements from a totally ordered universe and rearrange them in ascending order. So for example, we want to sort all our songs in our library. So the way we would do this is to then sort each half of the set independently. And then we need to combine these two sorted sequences efficiently. So for example, if we have the word algorithms and we want to sort the letters in that word, we would split it up into two equal parts. And then we sort the left half and we sort the right half independently. So then we get AGLOR and HIMST. So that's what we get if we sort the two parts separately. And now comes the merge operation. So the merge is basically look at the front of each of these two parts and we take the first character. So then we compare A and H, and A comes before H. So therefore we select A, we increment the counter there. So now G is the first in the left half and H is still the first in the right half. Again, we see that the G is before H. So then we select G. We increment, so now we're comparing L to H. Here, H is better. Then we compare I to L. I comes before L, so we select I. So now we have LOR left in the left part and MST left in the right part. And then we just continue like this. So what we see here is that we do a linear operation. We only need to compare one pair of elements. And for each comparison, we can directly choose what is the next one. So this is then a prototypical example of divide and conquer for sorting words. Very nice. Okay, so the second example I want to use is the closest pair of points. So in this problem, we're given the task of given endpoints in the plane, find a pair of points with the smallest Euclidean distance between them. So this is a very important problem because it's used as a primitive in many other applications. For example, Euclidean minimal spanning tree, Voronoi, nearest neighbor, and so on. And here below you see an example of 2 points that are the closest. So of course we can find a brute force solution, basically for each point, compare it to every other point, and then finding the smallest pair between, among those, find the smallest pair. But of course this is very expensive, it's n squared. We can, if we assume that all the points are on a line, then we can find a solution in n log n, because then it's basically about sorting these points and comparing it to the leftmost. For each point, take the one next to the left and next to the right, and each distance there is the shortest one. It has to be the shortest one. So then we could do it. And what we now want to show is we can do something similar for the two-dimensional case. So what we do is that we first sort it on x-axis and y-axis. And then we can compare it based on this. We can also divide it into quadrants. So we can divide this into 4 quadrants. And then we can solve each independently. The problem here is, however, that we cannot do this in a way that guarantees a uniform distribution. So we can get a very skewed, in some sense, all the elements or all the points could end up in one of these quadrants, which means that this will not let us, it will not work because we cannot guarantee that it's evenly divided. So what we do instead is that we draw a vertical line so that there are n squared points on each side. So basically finding the position where to place the line in such a way that half the points are on either side. And then we can find the points, closest point recursively based on this. And however, then the tricky part here is the combination step. So how to find the closest pair with 1 point on each side. And then we return the best on the left-hand side, the best on the right-hand side, and the best on the 1 point on each side of this line. So here the interesting part is, of course, really this third step. So what we can do is that, assuming that we know the minimum distance on the left-hand side, we know the minimum distance on the right-hand side, we know that we only need to consider those points which are this far away apart from each other. So there is no point in looking for points that are, for example, in this case, more than 13 steps away from the center line, because the total distance between this pair of points still has to be below 12 to make a difference. So it means that we can then check only these points, and we also know that there will be, so we basically sort these points in this strip based on their y coordinates. So then we get this sequence that we see below, and then we actually only need to check a small subset of this list, and you can think about why that is the case. Yeah. So yeah. So basically, we then need to just check for each of these pairs what is the shortest, because here, of course, we have to remember that we have to combine the distance both in the x and the y direction. So it means that we only need to consider points that are closest. We know that either 1 or 3 is the closest to 2, because 4 and 5 and 6 and 7 are all further away. So therefore, we only need to check a small subset. So this is then an efficient way of finding the smallest distance where 1 point is on each side of this line. So here we then have the total algorithm, where we recursively, first we compute where the separation line is. So again, we just sort it on the x-axis. We count the number, so we just basically do a linear scan until we have found where we can place it. So the sum of all the points on one side is n.5. Then we draw this line, and then we compute the shortest or closest pair on the left side, the closest pair on the right side, and then we take the minimum of these, and we use that to then sort these points that are within this distance from L. And then we linearly go through this to update these positions. And then we return the smallest pair that you can find. So this is then clearly a n log n algorithm, which is then very useful and efficient. Okay, welcome back. So now in this the next part, I will talk about dynamic programming as one general technique for solving problems. So dynamic programming relates to, I mean, so far I've been talking about greedy, where we build up these solutions incrementally, basically doing locally optimal choices. Divide and conquer as a general approach to kind of break problems down into smaller parts that can be solved separately, and then combine these solutions to solve the original problem. So when we do this divide and conquer, very often what we do is that we need to solve the same sub-problem many times over and over again. And in order to deal with this problem where So we only compute each sub-problem exactly once. Then we can use this technique called dynamic programming. So it's very closely related to the divide and conquer, but here with the extra feature that we either store previously computed partial results, or where we set the order, could order these computations in such a way that we always only compute each thing once. So dynamic programming, the history is that Richard Bellman came up with this in the 50s. So basically it was used to solve planning problems. And apparently the Secretary of Defense was hostile to mathematical research, so therefore he called it dynamic programming instead. And this is a technique which is extremely widely used in many different research fields. And I mean, it's used to solve, again, a really large variety of different problems. Actually, we would see many solutions in this course where you have more kind of specialized algorithms, which are basically dynamic programming. For example, different types of graph algorithms like the Bellman-Ford shortest path algorithm as one example. So what I want to do now is to go through a particular type of problem, namely the weighted interval scheduling problem. So in this problem, we have j jobs that start at different time points and finishes at different time point. And each job has a weight or a value v. And two jobs are compatible if they don't overlap. So we basically have one machine that can do these things. So now we have to find the maximum weight subset of mutually compatible jobs. So what are the jobs that we could kind of accept in order to maximize the total weight or value that we get? So first of all, let's just try to do a greedy approach. So for example, consider the jobs in ascending order of finishing time. So basically you want to take the job that finishes the first, and you start with that, and then you take the job of the remaining jobs that you can do, select the one that finishes first, and this kind of greedy strategy would work if all the weights are 1, meaning that we want to take the maximum number of jobs. But in this case, we have weights, and then that approach does not work. So we can just give a very simple example here at the bottom. So we have two small jobs with weight 1 and one large job with weight 999. So the greedy approach here would select A because it has the earliest finishing time, and then it would select H because now it has the earliest finishing time of the available jobs that we could take. And that, of course, is much worse than just taking job B, which would given us the 999. So this does not work. So what we do now is that first of all, we order the jobs by the finishing time. So that the one that finishes first is called 1. The one that finishes second is called 2, and so on. And then we can just graphically see the different jobs in the picture below. So now they're sorted on the finish time. So P of j is the largest index I less than j, such that job I is compatible with j. So for example, the P of 8 will be 5. So because it has a finishing time that is compatible with 8. So it's the one right before, so to speak. So P4 is also compatible, but it's not the latest one. And P of 7 is then 3. So basically just look at the start time. You go upwards until you find the first job which has a finishing time before that time point. Next, we defined opt of j as the value of optimal solution to the problem consisting of jobs requests 1 to j. So this is given j jobs, what is the value of the optimal solution? This means that opt_n is now the value of the optimal solution of the original problem. And now we can see that in order to solve opt_j, we have two choices. Either we include job j, then we get the profit or the weight or the value of the j, vj, and then we also have to remove all incompatible jobs. So all jobs that you cannot do with this. And what we see here is also that this must include optimal solutions to problem consisting of remaining compatible jobs. But that's so this has this optimal substructure property, just like we have with the greedy. But anyway, and then the second case is that we do not include job j. But again, we have to include all the optimal solutions to smaller problems or problems before this. So what we now can do is that we can recursively define opt_j as 0 if we're before the starting point, because I mean that's the base case. And otherwise, we have two options of which we take the maximum. So we take the maximum of optimum, of vj plus optimum of p of j. So here we see that the next job, so to speak, that we can include. So this is a way to kind of the rest. So this is mean that we select this job, we take the profit from that, and then we have the optimum of the remaining jobs. Otherwise, we just skip this particular job and we take the optimum of the rest. And if we take the best of these two options, then we find the optimum. So what we now have is a recursive definition of what it means to select the optimal job. So what we now, of course, can do is that we can, for every possible combination, we can compute this. So I mean, actually, we can just set up a recursive definition. So if we run this program, we will compute the optimum value. However, the problem is that we now will compute the same subproblem very, very many times, actually exponentially number of times. So this is then extremely slow. So actually we can see the recursion tree on the right, just to see that in order to compute 5, we have to compute 4 and 3. In order to compute 4, we have to compute 3 and 2. And in order to compute 3, we have to do 2 and 1. So actually we can see this tree, subtree 2 are in 1, 2, 3 places. And the subtree 3 is in 2 places, and so on and so forth. So it means that we will redo all these calculations. And the whole purpose of dynamic programming is to avoid having to do these recalculations. So there are two ways of doing this. The first one is called top-down dynamic programming, or more popularly memoization. And what we do here is we basically create a memory, and then we populate this memory after we have computed the value first time. And when we need a value, we first check in our memory. If we have already computed it before, then we use that. Otherwise, we compute it. So what we get is that we need to initialize our array to be not computed. And then we check in order to compute optimum of j, we check is m of j initialized, or rather if it's uninitialized, then we compute it. And then we just do this recursively. And then of course we need to remember to store it in our memory. And then we just return the value from memory. So actually this change compared to the brute force solution is extremely small. The only thing you need to do is to add this memory, and remember to check if you already computed it. If you haven't computed it, compute it, and then return what's in the memory. So this is a very convenient and very easy way of doing it. And I mean, personally, I usually use this approach because that's the fastest to get correct. Yeah, and you can also check the actual runtime complexity of this. That's not super important for us. I would skip that. And then actually there's an interesting subproblem, and that is this opt will only compute the optimum value, not the particular sequence of, or rather what jobs to include. So in order to compute what jobs to include, you need to, to do it somehow. I mean, one way is to store a pointer. So basically, for each element in your memory, remember where you came from when you did this. So basically, in the whether you so that you build up kind of store in this database or in this table the values that you used. The other approach is to kind of compute it backwards. So you check, you basically check whether the value is equals to the value plus the optimum value of the rest. Then you add this job, otherwise you don't use it. So basically you just go through the memory one more time and figure out whether you used the job or not. So this can also be done. So second approach. The second type is, rather than top-down, used to bottom-up dynamic programming. So here what you do is you start at the bottom with the smallest subproblems, and then you successively build up larger and larger subproblems until you build up all the way up to the kind of largest problem that you want to be able to solve. So in this case, we can see that we start at the bottom, basically with the earliest finish times jobs, so P1. Then we can start with that, and then when we know the value of P1, or rather of optum 1, then we can compute optum 2, and so on. So by ordering from the earliest finish time to the latest finish time, and then computing in that order, we know that we're guaranteed to always have computed the value we need, because we're only looking to the left, so to speak, in this order. So this is a different way of doing it. So this is, of course, more efficient. There's no recursion. There's just a pure for loop. And so this is faster and less memory, needs less memory than the recursive variation. But you need to be sure that the order that you're computing is correct. And for some problems, this can be a bit tricky. But in many cases, it's quite straightforward. So that's one example. I also want to go through the knapsack problem, because this is a problem that is included in the labs. So in the knapsack problem, we're given n items and a knapsack. And each item has a weight and a value. And also our knapsack has a capacity, W. And now the question is, which items should we include in the knapsack in order to maximize the total value? So in this particular case, we have 5 different items. They have different values between 1 and 28, and they have different weights between 1 and 7. And in this particular case, our knapsack can fit 11. So for example, we could choose items 1, 2, and 5, which would then have a weight of 10 and a value of 35. Or we could select items 3 and 4, which would have a weight of 11 and a value of 40. Or, but we cannot select, for example, 3 and 5, because the weight of that is 12. So that's not a valid option. And here we can see that we can try a number of different greedy approaches. For example, greedy by value. Add the item with the maximum value. So in this case, we would select the 5 first. So now we have 28, and we have 4 left of capacity. That means we would select item number 2. That would give us 34. Now we have 2 left. And we can select item 1, and then we get this 35. So that's the solution you would get, greedy by value. If we do greedy by weight, we add the minimum weight item first, so that we select item 1, then item 2. So now we have 8 left. So then we would select item number 3. So now we have 1, 2, and 3. And now we cannot add anything else because we only have 3 capacity left, and no item has a weight less than 3. So in this case, we will only get 25 in value. So it's less than 35 that we got with the first. So actually, a better strategy is to go greedy by ratio. So basically, the value per weight unit. So here we would select item 5 first. Because it has a weight ratio of 4. So we will select item 5. And then, let's see, we only have 4 left. So then we need to select item 2 because it has a ratio of 3. And then we still have 2 left, so we can fit item 1. So actually we get exactly the same result as the greedy by value in this case. So actually this greedy approach would have been optimal if we could have taken fractions. So for example, if we cannot fit, for example, we can only fit 80% of the item. If we can then take 0.8 of this item, then this would be optimal. But since now we have to take discrete units, either all or nothing, neither of these greedy strategies are optimal. So again, what we do here, so here is a kind of a one attempt to try to do this. So for example, so what we need to do, for all of these dynamic programming problems, what we need to do is to define the state. And based on this state, that it should be sufficient to find a unique optimal value for that, and also that it's sufficient amount of information so to compute the optimal value for this particular state. So let's try using the state of the index I, so that we have the maximum profit subset of items 1 to j. So for example, optimum of 3 would be the optimum choice when we can use items 1, 2, and 3. So now we have 2 choices again. Either we include item item I, or we don't include item I. So in the first case, where we do not select item I, then we have to select the best subset of the remaining ones. And otherwise, we have to select the optimum when we include item I. But here, the issue is that if we only include this, there is not sufficient information to imply what other items we have to reject. So the issue here is that we don't know how much remaining weight we have. So of course, here's the hint. We need more subproblems, we need more state. And of course, what we need is to include a weight. So to solve the knapsack problem, we have a 2-dimensional dynamic programming problem where the 2 dimensions are the index I and the remaining weight W. So here, what this means is the maximum profit subset of items 1 to I, where the weight is at most W. And to compute the kind of goal here is to compute optimum of N and W. So N is the number of items and W is the total capacity of a knapsack. And again, we have these 2 choices. Either we do not include item I, for example, because it's way too much, or we don't want to use it. And in this case, W is the same, so we still have the same amount of weight left, but of course we need to reduce I with 1. So in this case, it's just optimum of I minus 1, comma W. Or we include the item I. So in this case, of course, we get the value B, but we also use the weight WI. So it now means that we need to select the best of the remaining items, but using the new weight limit. So if we put this together into a recursive definition, we can see that the optimum value of I, comma W is 0 if I is 0, because there is no elements to choose from. If the weight of this particular item is greater than the remaining capacity W, then we have no choice, but we have to return the optimal value of the remaining items and the same weight. In the third case, we have the option of either not choosing this item, and then W is the same, or we select this item, we collect the value, and we remove the weight from W, and then we find optimal choice based on that. So again, now we have this recursive definition, which would then allow us to do a straightforward recursive implementation. If we do that, we can then compute these values. So here we have an example of a bottom-up dynamic programming. So it means that we basically fill up this table that it becomes from the bottom up. So here we're only using values that we have computed before. So of course we need to initialize. So of course we initialize for any weight. For any weight, if we don't have any items, of course the value of that is 0. And then we go up in index from index 1 to index n, and we also go up from weight 0 until weight W. So we have a 2-dimensional loop here. And if the weight of item J is too much, then we cannot use it. So then we can initialize this item MIW with MI minus 1, comma W. So this is basically we're just taking this recursive definition that we had on the previous slide, and we just add it directly. And when we are done, we're done with these 2 loops, we can just return whatever in the memory at location n, comma W. Very nice and convenient. So if we just want to give an example. So of course, now the way we would calculate this is basically from the top left to the bottom right. So we will start with filling up in the first row. Then we would take the second row and compute that from the left to the right. And then the third row left to right and so on. So basically here it would be from top of the table to the top left to the bottom right. And we see that the answer to our query is in the bottom right corner. So what we also can see here is that if the value in the corner is the same as right above, it means that we are not including the item. So here it means that we will not include item 5, but we will include item 4, and then we now have used 6. So we know the weights. We know that we need to go to the row above, and the cell W equals 5, and there we see 18. And again, we see that it's different from the row above. Therefore, it means that we need to take this element. So it means that we take element 3. And now there's actually no weight left. So there is no choice but to not select any of the remaining items. So this shows how we can compute, and actually in this case also how to compute what items to include in your knapsack. And again, we can analyze the time complexity. So basically it is, as you would expect, it's the kind of number of elements, so the size of n multiplied by the size of w. So of course here what's interesting is that the larger the weight of your the capacity of your knapsack, the more computational expensive this problem becomes. So that's something to keep in mind. So that was my presentation of dynamic programming. You have also I sent out a number of options. There are more material if you want to read. So the final part that I wanted to say just a few words about is Monte Carlo tree search or Monte Carlo approaches. So what we have seen in some recent programming competitions is that you can have very, very large search problems, but you can use probabilistic techniques to actually deal with these. So basically the general idea is that you select a high number of random samples from the search space and then actually see if these are optimal. So you basically just, out of the really, really high number of possible choices, you randomly select a few and you see whether they are correct. And these are, for example, used in many different situations of ray tracing, physics simulation, actually scheduling, and game playing. So actually what we see, for example, this AlphaGo, this DeepMind's AlphaGo program, when they play Go, beating some of the human masters in Go, they use this technique called Monte Carlo tree search in order to explore the search space in a structured way, basically by selecting which branch to go down based on the probability that it will lead to a winning solution. And then you can use this to unroll a number of steps forward and add a strategic dimension to the value function that was learned directly from observing these games. And then learning this value function together with this Monte Carlo tree search then created a winning game strategy or gameplay. So normally this is not necessary for this course, but there are exercises that can be used with this technique. And if you want to solve harder problems and much larger problems, then this is an interesting technique. And again, it's something that we have been using in our own research. So actually, Fredrik Prentere and myself, we have a paper at this year's AAAI conference talking about using different types of heuristics together with this Monte Carlo search to find very good approximations for really, really large combinatorial optimization problems. So the summary of this lecture is that I've been talking about different approaches to solving problems. Starting with simulation, where you basically carry out the different steps, and including what we call complete search. So basically systematically going through the search space, potentially with some form of pruning. So you remove branches that cannot lead to optimal solutions, leading to this technique called branch and bound. And then I've been talking about greedy approaches where you can make locally optimal choices and achieve globally optimal results. Over divide and conquer approaches where we split up the problem into smaller subproblems, where you can recursively solve each of the smaller subproblems using the same technique. So we basically break it down until the problems become trivial. And then we put the pieces back together until we find the solution to the original problem. And one major issue with this divide and conquer problem solutions or approaches is that we often compute the same subproblem over and over again. And to deal with this, we introduce dynamic programming, both in the form of top-down or memorization, where we, after we have computed the value, we store it in memory. And before we compute any value, we first check if we have already computed it in our memory. then we just return from memory, otherwise we compute it. Or bottom-up dynamic programming, where we order the computation in such a way that we always know that we have computed the smaller problems before. So basically start with the smallest problems and then build up and create solving larger and larger problems based on these smaller problems that we solved before. And finally, I said a few words about using probabilistic search as an approximation technique to probabilistically solve even larger and more complex problems. So with this, I thank you very much for your attention and wish you the best of luck with solving problems in this course. Thank you.